Make sure to like and subscribe right now. Yes, do it.
Hello, this is Ron from MathX, and today we're going to be reviewing counting in states with this problem here with Frida the Frog. So this problem is a clear example of how to apply counting in the states. So without further ado, let's get into it. Frida the Frog begins a sequence of hops on a 3x3 grid of squares, moving one square on each hop and choosing at random the direction of each hop, up, down, left, or right. She does not hop diagonally. When the direction of a hop would take Frida off the grid, she wraps around and jumps to the opposite edge. For example, if Frida begins in the center square and makes two hops up, the first hop would place her in the top row middle square. The second hop would cause Frida to jump to the opposite edge, landing in the bottom row middle square. Suppose Frida starts from the center square, makes at most 4 hops at random, and stops hopping if she lands on a corner square. What is the probability that she reaches the corner square on one of the 4 hops? And the answer choices are here 9 over 16, 5 over 8, 3 over 4, 25 over 32, and 13 over 16. Okay, so now that we read the problem, let's figure out on how to solve this. So, our first step, I would say that's crucial in solving this, is kind of visualizing the problem, as I don't really understand what this whole thing means without a proper way to kind of visualize it. So, we're just going to quickly draw the 3x3 grid that Frida describes in the problem. So, we have the corner, edge, and center here. And now these are just the 3 distinct pieces that are going to be a part of it. So maybe let's label it real quick. So this would be a corner, this would be a corner, this would be an edge, this would be the middle, this would be an edge, this would be an edge, this would be a corner, this would be a corner, and this would be an edge. So now the next step we do in this problem is set up a state diagram. Now, a state diagram is essentially a sequence of events that will happen, and also known as states, as said in the title of state diagram, and it's a series of individual positions that it could be at a time. So, if that doesn't make a lot of sense right now, it will make sense when we start drawing our diagram. So, in the problem, it says that Frida starts in the middle. So, let's just draw these 3 circles to kind of showcase where Frida could be at a given time. Now, this would be the middle, this would be the edge, and this would be the corner. And now we label that in its specific way because it would have to go to the edge first to reach the corner, meaning the corner would be the last step. And also the goal of the problem is to reach the corner. So there would be no returning when you reach the corner square. But there would be a series of events between middle and the edge. So now let's kind of draw the lines here to kind of showcase what the exact problem is kind of representing. So it starts with the middle going to the edge automatically because that's the only place it could go. So we can just draw an arrow here representing that. So we have this arrow. It's not too neatly drawn, but I try my best. And then we have the edge to the corner. Now, default in this problem, the middle would anyways always go to the edge. So we can draw like a fraction here, but not really a fraction. It's just one probability, and the middle would always go to the edge. And it makes sense in the problem because Frida is always going to the edge, straight from the middle. So now that we have that drawn out, the probability that the edge that Frida is on goes to the corner would be 1/2, because it's always going to be surrounded by 2 edges, 2 corners, I mean. So let's just draw that here. 1/2 to get to the corner. But now, among this, the edge can be repeated several times. So let's just kind of draw that out here. See, I may have to restart this arrow because it's a bit bad. There, that's a lot better. So this will be representing how the edge can always go back to another edge by just simply with a 1/4 probability. So let's just write that out real quick. There we go. And it also can return back to the middle with a 1/4 probability. So let's also draw that. Alright, so now that we're finishing up this diagram, now we can start counting for the individual state pathways that there could be. So, 1 over 4 to return back to the middle. And that just makes sense because we can now, let's just go over why this all makes sense here. So the middle would be going to an edge no matter what. But from the edge, it has a half probability of going to another corner. And also, as it mentions in the problem, that if you go past an edge, you can always return back to another edge, going another hop and come returning to this side. So that will be a 1/4 probability of happening, and just returning back to middle will be a 1/4 probability. Now we can just calculate for the individual possible pathways. So the possibility that the middle would go straight to E, so that to the edge and then to the corner, would just be 1 times 1 over 2. Because the thing is, the middle's always going to an edge, and for it to just reach a corner, it will be arriving in the first 2 new moves. And that would be case MEC, where it goes to the middle. Well, it actually starts in the middle. It goes to an edge, which would be a 1 probability. So, and then it goes to a corner, which would be a half probability. So really, it's just going to be 1 times 1 over 2. The next possible scenario is where it continuously goes to 2 edges. So basically, it goes, let's say here, then it would go to here, and then it would go back to here, and then it would go to another corner. So that would be case MEEC, where it's going to the 2 edges before it goes to the corner. So that would be equal to 1 times 1/4 times 1/2. Let's just extend this out so it's more visually appealing. There we go. So now that's the second case. And let's also just compute for these real quick. So this would be equal to 1 over 2. This would be equal to 1 over 8. And the next case that is possible here is where it just continuously goes to more edges. And where it goes to the middle, and let's say it just goes, in this case, maybe left. So it go here, and then it go to this edge, and then it go back to this edge here. So just hopping all over the place. And then it goes to the corner. So in that case, it also just multiply by another 1/4. So let's just write that out real quick. MEEC. This would just be equal to 1 times 1/4 times 1/4 times, finally, 1 over 2. And that would be equal to 1 over 32. Now, our next case, which is possibly here, is that we'll have the middle, then go to edge, and then it go back to middle, and then go to edge, and then go to corner. So let's just write that out. MEMEC. And also keep in mind that even though the problem says at most 4 hops, even though it says 4 letters here, 4 and over letters, that's not necessarily the amount of hops. Really, the amount of hops will just be the letter amount after the middle, because the middle you're already starting at. But anyways, we can start calculating for MEMEC. So at the middle it's automatic, so we can do 1 times, so middle to edge will just be automatic, so just be 1. And then what we do is that we have the edge return back to the middle, so that'd be times 1/4, because it's essentially the same probability as going to another edge. And then from the middle, it'd have to go to an edge, so we can just do times 1. Similar to how we had a starting position from the middle to edge. And then after that, it would just be times 1/2. So really the probability here would just be 1/8. So let's just write this out, expand it here. There we go. Now, when we add all these fractions together, we know it's going to be in terms of 32. So we can just do 4 plus 4 plus 16 plus 1, and that would be all over 32. So we can just write that out, that would be equal to 25. But the final answer would actually just be 25/32. So let's just circle that. There we go. So there is an easy example of how we can apply counting in states to a problem. And despite it looking somewhat challenging, it really is not. And this concept can be used on many advanced problems. As this problem here was actually an AMC 12 problem in the high 20s. So pretty close to 25. And if you just solve this, and this took us maybe 5 minutes? So applying this trick is not that difficult. But I recommend you practice this, and you'll be able to also do counting states really well and basically solve them within seconds. Anyways, that's all for today. Thank you for watching and have a good day.